and welcome, I guess. Yeah, I did get a little self-conscious after like seeing my last video, so I put on a little makeup. Okay, yeah, because I know how to do it. Shut up. Anyway, let's talk about bacteriophages, and I realized that I did not talk about one-step growth curve in my last video. But anyway, let's talk about one-step growth curve and bacteriophages in this video. Okay, so these are my bacteriophage. We're gonna come. Bacteriophages are actually just viruses that can kill bacteria. Okay, so you might be like, Ashia, then are all viruses bacteriophages, or like are all bacteriophages viruses? Like, what's their deal? Okay, I want you to think of viruses as an umbrella. Okay, so you see like one part of like a segment of the umbrella is like bacteriophage. So bacteriophage is like one of the categories of viruses. Quick disclaimer, love how I just like randomly say it. Quick disclaimer, this video is made for revision purposes only, because I tend to learn stuff and forget them faster than the speed of light. That's why I make videos about it, and I watch myself embarrass myself in the internet, while also just like helping myself revise. So any like examples or connections used here is, to help me remember it, instead of like actual valid examples, because I just don't want things to get too technical, because I'm pretty sure I'll be watching this literally the day before my exams, or if we're lucky. And if we're unlucky, or if it's the usual thing, then 1 hour before our exams. So let's continue. Bacteriophages are viruses that kill bacteria. Now, what are their significance in like our lives? Now, remember antibiotics, right? So you do realize that we are becoming like very, very resistant towards like a lot of antibiotics. Anyone know why? Okay, I'll say that because I am one of the people who do that a little. I'm very guilty of that, but whatever. It is the misuse of antibiotics, as in not completing your courses, or like having antibiotics for every little thing. No, I don't do that. I just don't complete my courses. I have commitment issues. Shh. Anyway, so okay, how does an antibiotic work? Let's talk about that a little. So we have our QQ molecules and QS molecules. Let's talk about QS molecules, because that's supposed to come first, and I've sort of messed up initially. Okay, so QS molecule is signal molecule. I want you to think of it. QS, signal. So QS molecules, it's like it helps in bacteria like communication. Okay, so what antibiotic does is that it makes QQ molecules, as in quorum quenching molecule. It is as difficult of a work to do as much as it's like to say. I don't know what I was going for there, but you get it, right? So quorum quenching molecules, it blocks the quorum sensing molecules, and like does not let the bacteria just like talk to each other. And I'm sorry, in this generation, how do you expect me to live without social media? Like, this is exactly what antibiotic does. Like, dude, social media was inspired by this. So this is how it does. It injures and dissociates the bacteria, and like immobilizes it, blah blah blah. So you do realize that because of like the misuse of antibiotics, we are like right now facing MDR and SDR. Now, what is SDR? Once again, that was supposed to come first. But anyway, what is SDR? SDR is single drug resistance. That means I am resistant to one drug. It doesn't work on me. You know what resistance is? It's like getting used to abuse. That is it. So that means my body is just gonna get used to the abuse, and it's like the antibiotics are not gonna work. So imagine that happening to one antibiotic. That is bad enough, right? Except we are actually developing abuse to multiple drugs, aka MDR, as in multiple drug resistance. So in this case, how the hell are we just gonna heal whenever like we have like a bacterial infection? Of course, like ew. Ew. But anyway, how is that gonna happen? That's where my bacteriophage comes into the whole thing. Wow, it is like hot. I didn't even turn on the fan because of you guys. Like, anyway, okay, so what happens when what was I saying? Hold on. Yeah, how does bacteriophage work? Like, how does it work? Now, bacteriophage, it has, like, the significance of it is phage typing and phage therapy. Now, a little disclaimer, bacteriophage is also called just phage or like phage. I don't know, okay? I just decided to call it both, okay? So, phage typing. Okay, so when we're searching for something, like, you know, in the like the little thing, you know, we have like a PDF, and then we just like, don't ask me, I'm not tech savvy. We just like, you know, you type it out, and then, you know, you just like search it. So I want you to think of that, okay? So phage typing is like the identification of bacteria, okay? It is understanding. Yeah, it is an identification of bacteria, as in like it just like binds to bacteria, I'm guessing. That's how phage typing works. And phage therapy, like, dude, therapy, something we both need. But think of therapy. What does therapy do? Well, I realize whenever I get tired, this is how I start talking. But anyway, what does therapy do? Therapy heals us, I guess. So it's like, since it kills bacteria, we can just like use it. We have a common enemy, right? We can just like use it to our advantage, aka phage therapy. It kills the bacteria for us instead of us having to take drugs and shit. So phage therapy, it's a good thing, right? It is a good thing, except sometimes it can be turned into bad things. Okay, now let me explain how. I just need to find the slide that talks about phage therapy. I can't. Wow, I'm so lost. Hold on. Found it. Okay, so it's usually supposed to be like a good thing, right? It is a good thing. It kills. So for example, let me give you an example of like a phage which kills E. coli. It's T2 phage or T4 phage, not page, phage and coliphage, right? Now, it's a good thing, right? E. coli, doesn't it do food poisoning? I think it does food poisoning, right? So we're not gonna get food poisoning because of that, right? Except, do you remember that in our GI tract, aka gastrointestinal tract, there are E. coli that just like help with like gut stuff? The reason you don't poop your pants all the time, maybe? I don't know. Okay, so E. coli, there are good E. colis as well, right? So what is the good E. coli named? NiaCell 1917. Just like read this, okay? NiaCell 1917. It's got probiotic capabilities, aka I'm guessing good stuff. So imagine you're having a T2 phage because, you know, you got food poisoning, but that ends up killing your good NiaCell 1917 E. coli. Sounds like a wine collection, but anyway, it's gonna kill it, right? It's gonna have a bad effect. Maybe that's when you're gonna actually start pooping your pants. So, guess it's not a good thing all the time. However, it is still under research, maybe, that, you know, the bacteriophages are actually being designed by biotech people, aka future me, hopefully, to kill more than just one kind of bacteria, kill more than just one kind of E. coli. So there's that. How does it do? Whenever you think of like biotech, I want you to always like sort of like, well, the first thing to think of is our DNA, aka my robot DNA, aka my recombinant DNA. So it just does that. And well, what is the advantage of using my robot DNA? It is specificity, strain specificity. So imagine there's a new kind of new kind of bacteria that is like affecting every single one of us, right? Imagine. I need to like up my energy. Hold on, let me get a chocolate. We got the chocolate. I literally have to glue this every single time after I eat it, so my parents don't know that I actually unsealed the container. But anyway, so imagine there is like the specific bacteria. Why do you even need to imagine? Like, think of coronavirus except as a bacteria, okay? It's affecting a lot of people, and I would say like imagine like there's another strain of it, right? So like we already lived through a pandemic. We clearly like I'm sorry, I'm not gonna go through that again. Unless for the online classes, nothing was fun. Okay? So we already went through the first pandemic. We're already sort of like, we defeated my bro COVID-19, right? But imagine there is COVID-20. Now we're talking about viruses. Sorry, we're talking about bacteria. Okay, I know I'm using like COVID-19 as an example, but I want you to think of it as a bacteria right now. Okay, so if we take the same like phages or like the same big like antibiotics for what we took for COVID-19, of course it's not gonna work, right? Because it's like a different strain, right? So that's where phage comes to like the thing, okay? So it's gonna specifically target my bro COVID-20. Get it? You're supposed to get it. If you don't get it, I can't help you. Anyway, that was okay, yeah. We talked about all of this. Yeah. We talked about all of this. Now let's talk about more of the significance. Now, what are the significance in bacteria of phages? It is gene transfer in bacteria. Now let's talk about it because this is like a very important thing. Now I need you not to get confused here, okay? So there are two types, okay? Once again, let's come back to lysogenic and lytic because I studied this. Okay, so for lytic, what really happens is that the bacteriophage, it enters the bacteria and in the host cell, it enters the host cell, okay? It enters the host cell and it multiplies itself inside the host cell and it just sort of like infiltrates. I want you to think of it as like an army. Like, yeah, an army of like warriors entering and, you know, like taking over a country. Makes sense, right? That is like my lytic phage. I will explain the technical terms later. And then we have my lysogenic. Now, this is my favorite. Okay, now I want you to think of all my favorite movies, aka the movies I grew up with. So, Mission Impossible, James Bond. Okay, well, what is, like, you're getting it, right? These are spy movies. So what my bro phage does is that it enters the bacterial cell and just like poses as a spy, right? So it pretends to be one of the normal molecules instead of inside like the bacteria, and then it goes through one of the two possibilities. It either goes to it sends information and then, you know, it gets its army to come and then, you know, like infiltrate the whole thing. Either that, okay, or. So that means it either enters back to the lytic cycle, like lytic phage, or you know exactly where I live now. Anyway, so either that, or what it does is that it infiltrates, since it's like a spy. So it infiltrates the database of the system, and then it just like changes its system and just like remains dormant. Interesting, right? So now, okay, so this, let me now just like read the technical terms to you. Lytic phage kills bacteria instantly by inhibiting HGT, as in horizontal gene transfer, as in it does not do the horizontal, like the bacteria does not like replicate. It doesn't get to replicate. The virus replicates, but the bacteria does not replicate. But for lysogenic phage, which is also known as temperate phage, now there are 2 slides for this. Okay, temperate phage, what really happens is that it acts as a spy living in the bacteria, becoming prophage, as in a prophage, like professional phage, and then HGT occurs, as in horizontal gene transfer occurs. Phage is transferred to other bacteria, and either lytic cycle is like initiated, as in, or it enters a quiescent state, chilling inside the host cell, no making viruses, but just getting copied like every single time the bacteria is like replicating, it is replicating the bacteriophage with it. Get it? Yeah, of course you do. So yeah, that's what's happening. This is also like the prophage, the name for the prophage is also called an integrated or progeny mode. Yeah, so one of the examples of like lytic or virulent phage is T4. T4 phages, they go through lytic or virulent phage. Okay, phage therapy. Let's talk a little back about phage therapy because I missed it. Okay, so this is what bacteriophage looks like. You see, it looks like a nanopod, right? Okay, so first things first, phage therapy is also used by nanobots. Still under research, but you get the whole thing. Okay, this is my head, as in like the capsid and blah blah blah. This is the tail. These are contractile sheath. This is my tail fiber, like these little limbs. Not cute, but like you get it. And then we have like the base plate. Now these little yeah, okay, this is the collar, by the way. It's not labeled, but this is the collar. So that's it for the phage introduction, I guess. Now we talked about this, right? So the whole lytic, lysogenic phage, yes, we talked about it. Now let's talk about essays. Like not essays that we write for English, rather like essay, like how are like bacteriophages. So we know that when we're gonna observe, when we're gonna absorb, shut up. Anyway, when we're gonna observe a bacterial multiplication, so what are we gonna do? Like, how are we gonna observe it? Like for bacteria, we can just like use the culture and like look through it. But for viruses, what we do is that we make two-way plating system. Now this is called a plaque assay. Okay, I'm just gonna show you the spelling here. Plaque assay. Now let's read the whole thing. It's a two-way plating system. Why is it a two-way plating system? The first, okay, let's talk about the why later. Let's talk about what, okay? the first layer is of bacteria. Okay, as we know that the virus, it eats bacteria, so we just gotta bait it. Okay, it's like hunting. We gotta bait it. Hold on. So we know that bacteriophages, they eat bacteria, right? So that's why we gotta bait them. So the first layer of like the essay is gonna be the food, aka bacteria, and then the second layer will be virus, a bacteriophage. So first, the bacteriophage and bacteria are mixed in the molten agar and poured on the agar layer. The PFU, as in plaque forming unit per milliliter, is then counted, and then which pretty much like measures the infectious unit. That is how we observe the phage thing, and different media component is used because like the conditions for bacterial growth is not going to be the same as like the conditions for the bacteriophage. That's why they are different. The media components are different. So moving on to the one-step growth curve. I really want to talk about it because it's a very important thing to talk about. So what is one-step growth curve? It is like the growth curve for bacteriophages or bacteria. This is what it looks like. Get it? So this is my eclipse period. This is my rise period, and this is my plateau. Okay, so the eclipse period, actually this should be named as like the latent period, okay, instead of the eclipse period. Okay, I'm feeling shy again. This should be named as the latent period instead of the eclipse period, because the latent period, okay, the eclipse period is, okay, I don't know why. Let's talk about what really occurs here. So here the viral adsorption occurs. Now, if you remember this diagram properly, okay, so I want you to think of it side by side. The adsorption, penetration, uncoating, and then the transcription, translation, all the way up to here. Okay, all the way up to here is what occurs in the eclipse period. Sorry, the latent period. Okay, and this is where the intracellular virus like happens. Okay, that means the virus still doesn't leave the host cell. Okay, the reason why it's like just like there, okay, along with the axis, because it takes time for the viral infection to happen. Okay, it's very classy. It's very classy. That's why it takes a lot of time. So for that attachment, penetration, and all that crap, it takes a little time. So then after it's done, okay, this is the point where all the extracellular viruses begin to form. So the number of viruses tend to rise. Okay, so like you see the whole rising thing. Oh, by the way, this is infectious units per host cell. The y-axis and the x-axis is time. Okay, so the rise happens, and what happens in the plateau? What really occurs in the plateau part? It is when no more viruses are liberated. That means no more virus. So in this thing, in the red part, virions, as in like I'll talk about virions later. Just give me a little moment. Virions are released here. Virions are not released here. Virions are maybe not released here. So you get the whole thing, right? The reason viruses, they don't have a death phase is because that purely depends on the host. Get it? That purely depends on the host. And viral maturation also happens in the rising period. Get it? And the first virion escapes, like the escaping of the first virion is the whole extracellular, like leads to the whole extracellular thing, and it is that is like the statement, the thing that ends the latent period and the starting of the rise period. Right? So that was one step growth curve. I feel like I just condensed it a lot, but it's okay. Now let's talk about latency. Now you know what latency is? It is like it's like the latency. Why am I explaining it, dude? Okay, so this is the latent period. Remember? So latent means hidden. Like we all heard about latent heat, right? So latency is when the bacteria is in there, but it's like hidden. So latency period depends from virus to virus, right? But let's talk about two examples. One is herpes, the other is chickenpox. We all got chickenpox, right? Not the KFC kind, but you get the whole thing. Chickenpox. Now, chickenpox is caused by the virus varicella zoster. Varicella zoster. What does this chickenpox cause? Rash, itching, pain, blah blah blah. Why is it dangerous? So this virus, it affects the nervous system, and it remains dormant for many years. So let's just say I got chickenpox, right? I have like the virus. There is a chance that I might not be showing the symptoms, aka rash, itching, all that crap. But I still may be carrying the virus. That means it's latent. It's still taking time for infection. Now, if I'm not wrong, the reason for latency could be because of like how strong the immune system is. Now, this is a completely me-to-me connection, okay? Feel free to disregard it or just like correct me in the comment section if I've made any mistake. So there's that. And then we got herpes virus, okay? Herpes virus, it also affects the nervous system and remains latent without any symptoms, right? So how does it like transfer? It transfers from skin to skin contact and from like mother to fetus, and the most like few examples of it is genital herpes, aka herpes simplex 2, and herpes simplex 1 causes cold sores or fever blisters, which is more dangerous, more in infants, which is transported from mother to fetus. The herpes infection lasts a lifetime. Do not get herpes. Like literally do not get herpes. Now for the last part of like the whole thing is virions and prions. What are virions and prions? They are not organisms, but they're pathogenic. Let's talk about virions first. Virions are small circular RNA molecules without a protein coat. So you're talking, I think a protein coat is exactly what maybe makes a virus its living characters. So maybe that's why viroids, it's not virions, viroids. Viroids are considered completely non-living. Take a sec. It mostly affects plants. It also infects humans. For example, viroid like hepatitis D virus for humans, HDV. And for plants, there was the potato famine in Ireland causing a late blight, which is a disease which destroys both roots, like edible roots, tubers, and leaves of potato plants. Now, viroids, these resemble introns, which are non-coding sequence of a gene, okay? Which, if it were cut, like introns, if it were cut out of the eukaryotic DNA, they would look like they would resemble viroids, okay? They can fold into secondary protein structures, but they don't code for anything, okay? They're just infectious. Then we got prions. Prions are actually infectious proteins. So if you thought bacteria and viruses are like the only thing that you should be concerned with, you're wrong. Prions are infectious proteins. They're normal body proteins. So it's like the protein catching fever, okay? So the prions, how are prions formed? Prions are only formed when they come in contact with other prions. So that's what happens. They have no DNA or RNA. The main protein involved in human and mammalian prion diseases are called PRP. Okay? A little bit of that definition for prions again. Misfolded proteins that can make normal proteins misfold. It's like a bad influence in your life, but in forms of proteins. What kind of diseases does it cause? Mad cow disease. Okay, it infects the neurons, and it's called mad cow when it's done to a cow. However, did you ever hear the tale that, a lot of older tribes used to have the brains of their enemies? Remember that? Okay, so imagine, like I said, so I want you to think of this as like that. Someone, like a person A, had beef, okay? Beef, like the cow from which the beef came had mad cow disease, okay? So my bro is now infected with mad cow disease, but we're not gonna call it mad cow because we're not cows. So he got infected with a kuru disease, right? So he made super bad enemies, right? So his enemy killed him and then had his brain. So wow, it's very Dahmercore. But anyway, so the enemy got the kuru disease. That's how kuru diseases are just okay. So what is the scientific name of mad cow disease? It's called bovine spongiform encephalitis. Okay, now bovine spongiform encephalitis. Bovine means cow, spongiform because it develops sponge-like holes in the brain, and encephalitis means a brain disease. Okay, what really happens is that prions form insoluble deposits in brain, causing neurons to rapidly degenerate. Okay, so this was it for kuru and stuff. This was the two examples that we discussed. Now let's talk about vaccines. Well, what are vaccines? It's like the injection of I would say it's like a trigger for your immunity system to work. There's 6 types that are discussed in this slide. One is live whole virus vaccine. Example, measles, mumps, rubella, MMR. Then killed whole virus vaccines, polio. Number 3, subunit vaccines, influenza A, influenza B. Number 4, recombinant virus vaccines, HBs, AG, rabies, herpes, simplex virus, also known as HSV. Number 5, anti-idiotype antibodies, DNA vaccine. Example, HBV, rabies, Newcastle disease virus, reovirus, and poliovirus. Number 6, DNA vaccine. Example, HIV, influenza, herpes, simplex virus, T-cell lymphoma virus. Now to explain, very simply, I'm not just going to go through the technical terms, I'm going to explain the whole thing to you. Live whole virus vaccine. It is like a tiny, harmless coach for your immune system. What really occurs here is that live, almost or completely devoid, like its pathogenicity is cut off. I want you to imagine it something like that. Okay, it's introduced to our cell, which is capable of replication, but the whole virus is used just to test if our immune system works. Number 2, killed whole virus vaccine. So the virus here is dead, okay, cannot replicate. So the immune system is it sees it, learns to fight it, but the virus cannot make us sick. So the virion, how is it killed? The virion coat, the virion coat is intact, but the replication capability is destroyed. That means it cannot replicate. It cannot make us sick. Number 3, subunit vaccines. It is like presenting the enemy, okay, as it's like presenting the enemy's head to a country to make them train for what they're gonna go for in the war. Okay, so what really happens here is that a specific protein of a virus is administered. So to explain, piece of virus, as in maybe the spike proteins, we talked about spikes in my first video. It is like input, so every single bit of the virus does carry a little bit of the virus. So it will train our immune systems to just fight it, okay? Then we have recombinant virus vaccine. Now, whenever we talk about recombinant, let's talk about my robot DNA, aka our DNA. So a harmless, maybe DNA. Okay, specific protein of a virus is incorporated into a non-virulent virus. That virus is incorporated into the host. Get it? So a non-pathogenic virus is mixed with a pathogenic virus to test how well our immune system reacts. So it can learn to fight it and shit, right? So number 5, this is my favorite, anti-idiotype antibiotics DNA vaccine. Now, whenever I think of this, okay, I want you to imagine, okay, I don't know if you've watched, okay, of course you've watched it. We've watched Brooklyn Nine-Nine, right? So remember initially Terry did not want to go to the field because he was afraid of what he might do, right? Because he was really afraid after having 2 kids. So there was a scene where he just randomly shoots a mannequin a lot of times. I was like, what an idiot, right? So I want you to imagine that, okay? It's like training the brain with a mannequin instead of the real thing. So what happens here? The antibody raised against an idiotope and injected into host. It's like a puppet virus to train the immune system. Okay? Mimics the virus shape. Oh, for the recombinant virus vaccine, the virus is harmless, although hybrid, but still harmless. And for number 6, DNA vaccine. So what happens is that the enemy blueprints for training, immune system uses that to, okay, so imagine us taking the tactics that the enemy uses and then using that to train ourselves to become stronger. That is exactly what DNA vaccine does. DNA coding for the foreign antigen is directly injected into the host, and foreign antigen is directly produced by the host cell, producing the foreign protein, which serves as the AG and stimulate the immune response. I know you got it. So these are the preventions. Now, preventive measures for vaccines are usually taken for like 14 to 40 days. And let's talk about treatments. This will hopefully be our last slide. Treatments include interferons, antiviral drugs, and protease inhibitors. Interferons are naturally occurring proteins that are made by cells to fight off virus. So whatever proteins my body makes to fight off the virus is actually interferon. It usually destroys tumors as well. For number 2, antiviral drugs, for example, AZT, which is azodothymidine or nucleoside. So it is a nucleoside that reverse transcriptase inhibitor. It stops the retroviruses from copying their RNA into DNA inside the host cell. It just stops the whole replication thing. Get it? And then we have protease inhibitors, which pretty much just like stop the formation of capsid. So that's it. I know at the end I became a little tired, but hopefully you understood the whole thing.